Welcome you to today's lecture, and it is about deadlock. Now, what is deadlock? The permanent blocking of a set of processes that either compete for system resources or communicate with each other. A set of processes is deadlocked when each process in the set is blocked, waiting an event that can only be triggered by another blocked process in the set. Permanent because none of the event is ever triggered, because they are waiting for each other. So there's no efficient solution in general case. So before going to looking deadlock, we look at the resources categories. We have two types. One is reusable, other is consumable. Reusable is that can safely used by one process at a time and is not depleted by that use. For example, we have processors, we have IO channels, we have main and secondary memories, we have devices, data structures such as files, databases, and semaphore. Consumable means that one that can be created, produced, and destroyed. We have interrupts, signals, messages, information, and input-output buffers. Now, deadlock approaches. There's no single effective strategy that can deal with all type of deadlocks. So there are three approaches. One is known as deadlock prevention, means that disallow one of the three necessary conditions for deadlock occurrence and prevent circular wait condition from happening. Second is the deadlock avoidance. Do not grant a resource request if this allocation might lead to deadlock. And last one is deadlock detection. Grant resources request when possible, but periodically check for the presence of deadlock and take action to recover. Now this is an example of resource allocation graph. So look here, we have a circular is represented by process and square is represented by resource. So for example, P1 is requesting a resource in figure A. In figure B, a resource A is held by P1. So if you look here in figure C, we have circular wait. Here P1 is requesting a resource RA that is held by P2, and P2 is requesting a resource RB that is held by P1. So this is known as circular wait. And in loss, if we have a multiple instance of resources that can be allocated to P1, P2, so there's no deadlock in that case. So D is an example of no deadlock. Now we discuss the conditions of deadlock. There are three necessary conditions. So first one is the mutual exclusion, means that only one process may use a resource at a time. Second is hold and wait, means that a process may hold allocated resource while waiting assignment of other resources. And third condition is no preemption, means no resource can forcefully remove from a process holding it. And the fourth one is the circular wait. A closed chain of process exists such that each process holds at least one resource needed by the next process in the chain. Now deadlock prevention strategies. So design a system such a way that deadlock is excluded. There are two main methods. One is indirect and other is the direct. Direct means that prevention the occurrence of the three necessary conditions that we discussed in previous slide, and the direct is the prevention the occurrence of the circular wait. Now deadlock condition prevention, we have mutual exclusion. So means that that is allowed mutually exclude resources by the OS. And the second is that hold and wait can be prevented by requiring that a process request all of its required resources at one time and blocking the process until other requests can be granted simultaneously. Now the third one is the no preemption. If process holding certain resources denied then further request, then process must release its original resource, so that third condition not occur, otherwise deadlock will occur. Now the last one is circular wait. The circular wait condition can be prevented by defining a linear ordering of the resource types. Now deadlock avoidance means that allows the three necessary conditions but make judicial choice to assure that the deadlock point is never reached. So a decision that made dynamically whether the current resource allocation request will, if granted, potentially lead to deadlock. allows the three necessary conditions but makes judicious choice to ensure that the deadlock point is never reached. Required knowledge of further process request. Now, two approaches normally used for deadlock avoidance. One is resource allocation denial, other is the process initiation denial. So resource allocation means that do not grant an incremental resource request to a process if this allocation might lead to a deadlock. Second is that do not start a process if its demand might lead to a deadlock. Now, resource allocation denial normally done through Banker's algorithm. In Banker's algorithm, a state is defined as the state of the system that reflects the current allocation of the resources to processes. Now, there are two types of states. It has two types. One is safe state, other is unsafe. Safe means that is one in which there is at least one sequence of resource allocation to processes that does not result in a deadlock. Unsafe means is the otherwise, that is not safe. So let's see how this means. For example, here we have four processes P1 up to P4. We have resources R1 up to R3, and we claim matrix C is represented here on the left top. So here P1 requires three resources of R1, R2 has two resources, and similarly for R3 has two resources. Similarly P2 6 1 3. Now the initial allocation that is shown in matrix A, where P1 is allocated resource 1 is 1, R2 no resources allocated for R2 and R3. Similarly P2 is 6, R2 is 1, and R3 is 2. Now the need matrix to complete all these processes is shown C minus 8, that is need matrix, that is just subtracting from the claim matrix from the allocated matrix you get the need matrix, that is 2 2 for P1, similarly 0 0 1 for P2, and P3 is 1 0 3. Now the resources, the total number of resources is shown in the row. R1 is 9, R2 is 3, and R3 is 6. Now after allocation, initial allocation, the available resources for R1 is 0, R2 is 1, R3 is 1. Now look here, is this state is safe or not? So this is the question that we have to answer. How we answer this? We defined in previous slide that safe states means that there's at least one process that can be completed. So look here, if we allocate, we want to complete P2, we can do it because it requires only one resource of R3 and we have it. So this means that this is a safe state. Now next slide, we provide this to P1 and P2 is completed. When P2 is completed, that resources is returned to the available pool, that is 6 2 3 here. Now P2 is completed. Now the next we can complete P1 here because P1 required 2 for R1, R2, R3, and we have R1 6, R2 2, and 3. So we can complete P1. When we do that, again available resources are available. So look here, P1 runs to complete here 0 0. Similarly we can run for P3 and P4. Now this is for P3. Look here, P3 is run and we have the available resources. At the end we can easily accommodate for P4 in this case. Now the last slide here, we look at the unsafe state. So look here, now this is again we have 4 processes, 3 resources. Now we allocate resources differently this time initially. Now we have this need matrix. Now this is again we have the maximum resource of R1 is 9, R2 is 3, R3 is 6. Now available resources 1 1 2. Now if you look at the need matrix and compare with the available resource, can you provide these resources to complete one? Anyone? So look here, if we look for P1 here, we are unable to complete for P1 here. So P1 requires 1 unit each of R1. So this means that you can't complete for process P1. So this is an example of unsafe states. Okay. with available resources, because when you do the allocation here, available resources are 0 1 2 and required is 1 2 1 here after initial stage. So this is the problem. So this means that this is an unsafe state. So this is all about deadlocks and Banker's algorithm. And Banker algorithm actually works to how you can allocate the resources so that deadlock is not occur. Thank you.